Hello, my name is Mirko Schäfer. I'm from the Department of Sustainable Systems Engineering, INATEC, at the University of Freiburg. And this is joint work together with Anke Weidlich, also from INATEC in Freiburg, and Bo Tromberg from Entro Labs in Aarhus, Denmark, and Dave Jones from Amber, London in the UK. And we are presenting our research on the topic of tracing carbon dioxide emissions in the European electricity market. So the underlying question which we try to address here is simply, what is the emission intensity of your electricity consumption? So we all know that electricity generation from power plants is associated with emissions, carbon dioxide emissions. And why you now want to know what the emission intensity of your consumption is. So imagine, for example, you have a system with storage and flexible demand, and you want to reduce your carbon footprint as much as possible. Then you want to have a signal how the emission intensity of the electricity coming from the grid at each moment in time actually is, to schedule your system according to this signal. Or imagine you have a country which tries to fulfill certain climate goals and wants to reduce its emission intensity. So, for example, by building a lot of wind power plants and has a low emission intensity from their generation, but this country could be a net importer of electricity. So importing electricity from other countries, maybe this electricity originating from coal power plants, so being associated with higher emissions. So the challenge is to get these consumption-based emission intensities right. And there are several points which you have to address. So first, the emissions as a source. So how much carbon dioxide emits a power plant actually. And then the temporal resolution. So you want to have a clear signal. So you want to know what is the emission intensity of your electricity consumption right now. So you don't want to have an emission signal which is the same all over the year, which is somehow an average, but you want to have a high temporal resolution to feed this in, for example, in your scheduling problem. And you also want to have this consumer's perspective. So if you look at these pictures and you see an offshore wind farm and a power plant, and imagine you would be located far away from the coast and this coal power plant would be nearby, then somehow you would have the intuition that the electricity which you are consuming, which you are taking from the grid, is originated from this nearby power plant and not from some far away offshore wind farm. So for this consumer's perspective, we have to look at the system. We have to integrate imports and exports and transmissions over the grid into the picture. And that is exactly the topic we are addressing with this contribution. So here we are building on previous work, because in order to get a good signal about your consumption-based in emissions intensity, you need to connect the location of your consumption with the location and so the origin of the electricity. A method for that has been already proposed in the 90s. So for example, by Bialek, this paper Tracing the Flow of Electricity, where he proposes a simple tracing methodology which is connecting the origin, so the power generation source, by following the power flow through the grid to the location of consumption. And this methodology has been adopted by recent work by Tromberg and collaborators, or De Chalendar and collaborators, by applying the same thing now for emissions. So following the emissions from the source through the network to the point of consumption. So this has been done for the European system by Tromberg and also the electricity map, and by De Chalendar and his colleagues for the US system. So you get, using this methodology, you get a very clear signal. So you get consumption-based carbon dioxide emission intensities, but there are a lot of sensitivities involved. So, for example, the power system data. How good is your data and how detailed is your data on generation, load, and power flow patterns? How high is the spatial and also temporal resolution for that? And then the emission data. So do you have emission coefficients per technology only for a certain area or country, or do you have information of the about the emissions per unit, so per power plant? how good is your temporal resolution? Do you have these emissions coefficients on average for a technology, for a country, or do you have it for individual hours based on the actual generation? And what kind of emissions are we talking about? So you could say, okay, that's only emissions associated with fuel combustion, or you could also take emissions based on life cycle analysis. We take, for example, emissions associated with maintenance, upstream emissions, or embedded emissions in the infrastructure into account. So besides the sensitivities based on the emissions and the power system data, there's also a sensitivity to how you do the tracing, so to the allocation method. And this is what we are here tracing, that is a way how you couple the generation and load to the network. In order to understand that, we show you a very simple example. So here we have 5 nodes, 1 to 5, which could be, for example, now regions or countries in an overall electricity system. And each of these nodes has some internal generation, which is here with a plus sign, and an internal consumption or load, which is here with a minus sign, so the right bar. And in our system, we have 2 types of electricity. So we have the gray one and we have the green one. And we also have all the total generation, we have the total consumption inside the nodes, and we have the power flows over the system. So our input is the type of generation, is the load pattern and the power flow pattern. And what we want to achieve using this method of load tracing is that we want to know the composition of the consumption of electricity at the nodes and also the composition of the power flow. Because once we know the electricity mix which is associated with the consumption, we can use emission factors and translate that into emission intensities. So the first way to do that is a method called direct coupling, and that has, for example, been applied in the works from Desjardins and also by the electricity map. And here you couple the generation as well as the load directly to the grid. Okay, so we are feeding here 4 units of gray power into the grid, into node 1, and then taking out 3 units into your consumption or your load, and you're moving 1 unit over the grid to the next node. And down here you're doing the same, you're feeding it 9 units, you take 3 out, and you're moving 6 units to the next one. Okay. Now here at the next node, we are also now feeding in 5 units of gray power from the generation associated with node number 3. So here we now have to mix 6 units of green power with 6 units of gray power. So we know that here we now have a composition which is 50% for the electricity in node number 3. And we also know the electricity mix associated with the power flow from node 3 to node 4. And then we move on with this procedure. So we are now adding here 4 units of gray power at node 4 and get then the mix with this, which is here fed into the consumption at node 4, which is here transmitted to the next node in our system, and here finally mixed with the generation at node number 5. And then we have all the decomposition of electricity consumption based on these 2 types of power in our system and also the composition of power flows. So that is the information which we then can translate into emission intensities using coefficient factors. But actually you could do that differently. So if we go back to the start and look at our input data, we could also say, instead of coupling the entire generation and the entire demand of a node to the network, we always first serve internally the demand by local electricity and then only couple the remaining net export to the network. So that is a methodology which we call aggregated coupling. So here you see we first serving with 3 units of gray power the internal demand and then connecting the 1 unit of net export to the network, and the same down here with this 6 units. And then here at the next node we immediately see the change, because now the internal generation is serving the total load here and only 1 unit is the net export, which is here connected to the network, to node number 3. And then we get a different mix here. At node number 4, we have a transient node. So here there's no net export or no net import. So this is not coupled to the grid at all, and the power flow is just transported over node number 4 to the next one, where it is again coupled here with the net import with the electricity consumption. So this aggregated coupling leads to different results than the direct coupling. You see that here on the left side. And I want to emphasize that the input data and the overall idea of tracing the electricity to the grid is exactly the same. So it's really the choice on how you couple it. Both ways seem somehow intuitively, and both are somehow right, but they lead to different results. And they lead to different results because of several points. So the first point is that here for the direct coupling, you couple the entire generation and so the entire power mix to the network. Whereas in the aggregated coupling, you only couple the net export to the grid. So the net export could have a different power mix than the total generation. And then there's a difference in how you account for internal generation. So for example, here in direct coupling, you see that the internal generation is first coupled to the network, mixed with incoming power flows, and then you get a mix into the internal consumption. Whereas in the aggregated coupling, you first serve your local consumption, and so you have directly the same emission intensity as this net exporting node. And there's also a change for transient flows. So you see here that also we have here no net import or no net export, that the internal generation is coupled to the network and it's again mixing with the incoming power flow, and then this composition of the electricity is determined by all these influences. Whereas down here, as we discussed before, if you don't have any net imports or net exports, the node is, so to speak, decoupled from the network, and the composition of the internal consumption is not affected by the power flows at all. We applied both methodologies to data for Europe, so for 30 European countries, hourly generation data and load data and power flow data, and we calculated for each hour the consumption-based emission intensity for each country. So taking into account this flow tracing, this imports and exports, but in one time we used the direct coupling, and in the other time we use the aggregated coupling. And then we compared here the results, and we see that for a big country like Germany, the difference is very, very small. And that is because for Germany, the internal generation is very large compared to all the imports and exports. So that it's not so much determined by the exact choice of the methodology. Whereas for smaller countries like Denmark here in the north, or like Austria here in the south, they are smaller countries and they have a high number of transient flows. So here you see that this methodological choice on how you do it really changes this result significantly. So as a conclusion, we have to say you can come up with these very clear consumption-based emission intensity measures on an hourly basis even. So this can serve you as a measure of the emission intensity associated with your electricity consumption at the point where you are in the network. But in order to do it right, what you need to do is that you really understand the methodological choices you're doing, and you have to make them very transparent so that you know exactly how these things work. Our next steps are now that we expand this analysis further to the European system, and that we're also looking forward to collaborate with Jacques de Chalendar to take the same analysis on the US system as well. So first trying to improve data quality, so the power system data, but also the emission data. And then also to take a closer look at this difference between the direct coupling and the aggregated coupling in the tracing methodology. So we learned from Jacques de Chalendar that this might play an even bigger role for the US system, because there you have a lot of these transient flows or these transshipments, where this choice of methodology makes a big difference.